So today we shall be talking about hypothesis testing in Stata, part 2. The first part was done last week by Prof. So today we shall be considering one-way analysis of variance and two-way analysis of variance. So what is the analysis of variance? An analysis of variance is a technique for breaking down the total variability that we have in a system into their component parts. So when we say variability that we have in a system, you know, when an experiment is conducted, you have your treatment that have been applied to a subject or an experimental material. When you apply it, you're expecting a response. That particular process will generate a lot of things that will bring about a lot of variations. So when you say you have treatment, the treatment can be in levels. For instance, if you are talking about the effect of a fertilizer on the yield of yam, that fertilizer now, maybe it has a 3 levels. You have just nitrogen fertilizer, then you also have phosphorus fertilizer, then you also have the one for potassium. Those are the 3 levels. So, and you have your piece of land that has been divided into plots. So you now apply in a random fashion those fertilizers at different levels to the different plots. So by the time you do that, so many things are introduced because you're talking about different levels of the fertilizers. So now when you are done with the experiment and you have taken all your observations, you have recorded them, then you want to be able to categorize the variability that are present in that system into their component parts, that these are the ones that are due to the application of the fertilizers. And those ones that you are not able to fix, they are the ones that we call the random error. Whether you know the source of the error or you don't know the source of the error, whether you can control for the error or you cannot control for the error. So what ANOVA does is to break down the total variability that you have in the system into its component parts. So the other time, we talked about independent samples t-test, 2 sample t-test. We talked about that. This ANOVA is an extension of that independent sample t-test. You know, that one is for 2 groups. When you have this analysis of variance, it involves at least 2 groups, but most times we don't use it for 2 groups. We go for our independent sample t-test for 2 groups. So when you have 3 or more groups, we go for ANOVA. So what are we trying to do? We are trying to determine whether there is a statistically significant difference between the means of 2 or more independent groups. So if we have groups, 2 or more independent groups, in that case, those groups now, they are the groups that are categorical in nature. They are categorical in nature, and then you have applied whatever, and you have taken your responses on them. So you want to know whether there are differences among those groups. Which of the treatment is contributing those differences? Which one? That is what we want to talk about. So one-way ANOVA will help us to know whether or not there is a statistically significant difference between the means of 2 or more independent groups. So under one-way ANOVA, that is the simplest form of analysis of variance, it has just one factor or one treatment. It's just like our simple linear regression model or a simple number line. The only difference is that we have the error term included. So we have our y is equal to mx plus c, our number line from our secondary school mathematics. Y is equal to mx plus c, but this time around we introduce the error component because it is not a deterministic study. So that x there, that is the one factor. That one factor that we are dealing with, one way or one factor ANOVA, just one factor. So that one factor can now have its own levels. It can have levels. So that is what we have. So that one factor will have levels. You will break what you have down according to those levels. And those levels are what you will now refer to as the groups. There will be the groups, group 1, group 2, group 3. So under each group, you have your responses under each group. So it's not only agricultural experiments that you can use an ANOVA for. You can also use it for survey data. In as much as you are able to visualize, you're able to look at your data sets. Okay, you are looking at groups of students. You are looking at groups of students, maybe 100 level students, 200 level students, maybe you have identified something. Maybe you are conducting a test, intelligence quotient test. You are conducting intelligence quotient test. Then you have 100 level students for a particular department, 200 level students of the same department, 300 level, 400 level. You are conducting the same test, but you'll be able to group them like that. That's okay. These ones, they are given the same test, but these are 100 level students. These are 2, these are 3, these are 4, but they have been given the same test in a random fashion. So if you have that, you can also have a situation that you can use your analysis of variance. So what we are saying in essence is under one way and over, we have just one factor. And that one factor will be what? It will be categorical, to be categorical in nature. Then you have your dependent variable. The dependent variable will be a continuous variable, something you record, like your weight, height, scores, distance, those things that are quantitative in nature. That will constitute the dependent variable. And one way analysis of variance is parametric. So definitely that means that there are assumptions. There are assumptions that must be followed. So we have assumptions that the dependent variable should be continuous or quantitative. Okay. The dependent variable should be continuous or quantitative. Then you have the independent variables. Independent variables. The observations should be independent. Then apart from the observations being independent, can you see my screen, please?
Yes, we can, man.
Okay, so we are on assumptions of one way and over. We said the dependent variable should be a continuous variable. It should be quantitative in nature, as the 400 interval or ratio scale. The independent variable should consist of 2 or more categorical independent groups, just as we have said the other time. Then independence of observations. The observations should be collected independently to ensure that you are able to get that. That means that randomization must have taken place. You must take note of the random procedure and use it to the fullest, so that you ensure that you have independence of observations. Then the outliers, you take care of them. If at all you have outliers, they should not be significant, because if you have outliers, they will affect the results that you get from that particular modeling. Then the errors or residuals should be normally distributed. You get, when you fit your model, you have the response variable, you have the observations, then you have the one that be fitted. When you remove the one that has been fitted from the raw observations, you get the residuals. So the residuals should also be normally distributed, and then you should have homogeneity of variances for your response. Your Y's should have constant variance. Your Y's should have constant variance. So what we want to do now is to go to our Stata, and then we type web use systolic, web use systolic, web use systolic, web use systolic. Please type web use systolic. It's a data set from Stata, online data set from Stata. I hope you have done that. Web use systolic, just type it. Since you're online, it will bring it. Web use systolic. Web use systolic. So if we check that web use systolic now, you see that we have 3 variables.
It's not found on my. Hello, ma.
Hello.
Hello, ma.
Hello.
Please, can I see how you type the web use systolic?
Web use. Can you see my screen now?
Yeah. Okay. I'm okay, ma.
Okay. So if you, from your data editor window, you see the variables. You see drug. You see another one, disease. You see another one, systolic. That systolic is increment in systolic BP, blood pressure. So the first variable is categorical. You can see that we have 1. This is long format, 1, 1, 1, 2, drug 1, drug 2, drug 3, drug 4. 4 drug types. 4 drug types. We also have disease. Disease 1, disease 2, and disease 3. So we have two categorical variables there. So for one way and over, we said we will need just one factor. So we first of all deal with drug under one way and over. So we first of all deal with that drug that is in four categories: drug 1, drug 2, drug 3, drug 4. So the first thing that we talk about before we, the other time we said before we do anything, we run any analysis, we should first of all familiarize ourselves with our data set. So we try to check for those assumptions. So for the first three assumptions, for the first three assumptions, the first one says dependent variable should be a continuous variable. That one is from your study design. From the design of your study, you will have recognized that your dependent variable is a continuous in nature. So from that data set, that's systolic. Systolic is our dependent variable because it's continuous in nature. Systolic blood pressure. Then assumption 2, independent variable should consist of 2 or more categorical or independent groups. We said we are using drug as our independent variable. Should consist of 2 or more categorical independent variables. So you see that we have 4 groups there, 4 drug types there. So that one has also been satisfied. Then number 3, we have independence of observations. So the data has been collected using a randomization procedure. So that one will lead to the independence of observations. So from our study design, essentially, we have been able to ascertain, to check assumptions 1, 2, 3. Let us now move to assumption number 4. That is absence of significant outliers. Absence of significant outliers. To do that, let's first of all use our box plots. The other time we were on box plot, we were able to see some outliers. It's either we do that through box plot or through our summarize command. So if we want to check through our box plot, we just say graph, box, systolic, over drug. Graph, box, systolic, comma, over drug. So you can see the graph. You can see the graph now. You can see the 4 groups. You can see systolic BP. You can see for group 1, for drug 1, you can see that there is one outlier there. And that outlier is less than 0. It's a negative value. Apart from that, every other group does not present any outlier. So you can see that there's outlier there. And then you can also notice that the first two drug types, the first one is kind of lower. The second one, the median value is kind of higher. Then the third one, for the third group, it moves lower again when it gets to the fourth one. So you see that the variances, when you look at the length of the boxes, see that the variances does not seem to be okay, but we need to check. And you can see that there are variations. If you look at the boxes, there are variations because we don't know whether those variations are actually significant. There are variations among those groups, group 1, group 2, group 3, group 4, but we don't know. That is why we want to conduct our analysis of variance. So we have seen one outlier. So we don't know if this outlier is significant enough, or we should just go ahead. Let's check using our summarize command. If we look at our summarize command again, you see -6 under systolic. It is the one that seems to be that value that is far away that we saw the other time. You said it's a negative value. You see that minimum value now is -6. The maximum there is 44. So it's the value that we saw the other time. It's the only one that wants to potential trouble. So what we normally do is to check carefully what could have been the cause. Okay, another thing that we can do now is to continue with the analysis. Since that is the only one that we have found, we continue. But after the estimation procedure, we run our PP plots. When we run our PP plots, we look at the residuals from the PP plot and check for this particular value. If we're able to see that point again, if it is too far away, then it becomes a source of concern that we investigate further. Otherwise, we can just assume that every other thing is okay. So for now, we have examined our assumption 4 via the box plot and via our summarize command. So we still have to talk about assumptions 5 and 6. And these assumptions 5 and 6, we'll talk about that after the estimation, the model estimation. So the next step now is to try and get our estimates out. And we can do this using 2 approaches. The first one is by using the one-way command. The second one is by using the ANOVA command. We will first of all use the one-way command because that one-way command gives us the opportunity of conducting multiple comparison tests, multiple comparison procedures. It gives us the opportunity. But it does not permit us to run those post-estimation commands, those prediction commands after estimation. It does not permit us to do that. So if we want to check our assumptions, for instance, if we want to do model adequacy checking after we have concluded with the estimation, we cannot do that under the one way. We have to go and run using the ANOVA command so that we can now check whether our model is adequate. So for multiple comparisons purposes, we will use the one-way command. Then for prediction purposes to check our model adequacy, we will use the ANOVA command. So first of all, let us use the one-way command. Let us use the one-way command. So to do that from the menu, let's go to statistics. Statistics, linear models and related. Statistics, linear models and related. Then ANOVA stroke MANOVA. We have moved from statistics, then to linear models and related, then to ANOVA stroke MANOVA, then to one-way ANOVA. Statistics, linear models and related, then to ANOVA stroke MANOVA, then to one-way ANOVA. So you click, you see another window, one-way analysis of variance. I hope you are there.
I have a question.
Yes, quick one.
I have a question. You're kind of very fast. You said that one way is for multiple something. I couldn't get what you're saying about it.
You need just one factor. Just one factor.
Okay.
One factor, you can call it factor, you can call it treatment.
Okay.
You need that one factor. But that one factor, we have levels or categories. That one factor or treatment, we have levels or categories. So for instance, if you have one factor fertilizer, that fertilizer we have categories. There will be category for maybe nitrogen only, another category phosphorus only, another category potassium only. And then you randomly allocate these types of fertilizers, these levels, to your plots randomly, in a random fashion. Then you take your responses, you record maybe the yield of your crop, maybe cassava or yam or whatever. You record those for nitrogen only, you record under that. Those for phosphorus only, you record under that. Those for potassium only, you record under that. Do you understand?
Yes, sir.
So, and you now try to see whether there are, what are you trying to do when you perform an experiment? Your experiment is you apply something, you expect the response. You apply something, you expect the response. So when you apply your fertilizer, you expect the response in terms of the yield. Now, so you want to see whether your responses now, the yields that you have recorded, you have obtained, whether they are the same, as in the impact, the effect of nitrogen on your yield of yam is the same thing that the same effect that the phosphorus is also having on the yield of yam. It's also the same effect as the potassium is having on the yield of yam. You want to see whether there are differences or there are no differences. So the hypothesis we are testing there, that's the H naught, that there are no differences. They all have the same effect on the yield of yam. While the alternative hypothesis is that at least any pair, maybe nitrogen and phosphorus, or nitrogen and potassium, or potassium and phosphorus, any pair, at least a pair of them, there will be difference. So that is analysis of variance, the one-way analysis of variance is all about. Do you understand that?
Yes, ma'am.
Can I proceed?
Yes, ma'am.
Thank you very much. So
yeah, I'm sorry, ma'am. I want to ask a question.
Yes.
Although I've been trying to follow you, although I joined 15 minutes late, so I've been trying to do you send this note that we are using, or I don't know how to
Yes,
get
it is online. Go and get it from the classroom.
Okay.
Okay, thank you.
Hello everyone. So please, the lecture notes are available on the classroom. Please, you can check and then I believe the person that just asked the question, maybe I just joining for the first time, but the lecture notes are usually there, and everyone is encouraged to have them open or probably print them out so that you can follow.
No, it's not the note. I'm talking about the attached document to the Stata.
Just like web use historic.
The data set, okay, is online and you can access it from your Stata. As long as you're on this call, it means that you are online. If you can follow this class right now, it means you're online. So you just go to your Stata page and type, web use historic, as she has said. The data you will see the data set. Thank you, Dr. Kanko, please go ahead.
Okay, thank you very much.
Sorry, I want to ask something.
Yes.
I don't know if someone
Hello.
Yeah. I want to.
I typed it. You're telling me host not found.
Okay. I said I want to ask if someone can receive that.
Please, I can't hear you.
Mahamadi, we can't hear you. Can you speak up or maybe type your question, please?
Okay, I will type.
Okay.
Okay.
Thank you. So please, let's continue because of our time. So we have this new window now. We moved from statistics to linear models and related. From there, we moved to ANOVA stroke MANOVA. From there, we moved to one-way ANOVA. And then that gives us this particular window that we have here. So under main here, we see response variable.
Sorry, Dr. Tekwe.
Yes.
Sorry to take you back a bit. I think we have 1 or 2 questions on the chat box.
Okay.
Please, if we can look at the chat box. Let's quickly address them and then we'll continue until we now have some time again for other questions. So someone is asking, what is the conclusion talking about checking of the assumption 4? Another is what do you mean by factor? And the last is the person is saying that I think you might need to, Clementina Chinarom, you might need to unmute your device and tell us exactly what the problem is. You said you are lost. We need to know where. And you know, if, I don't know if you joined late or we need to know where exactly, you know, or what issues you're having. Thank you. So Dr. Tekwe, please, can you just respond to the first 2 while we wait for Clementina?
So on the assumption number 4, I said we will take our final decision after our model estimation. But as it is, we are proceeding with model estimation because we were able to detect just one outlier and it doesn't look as if it's significant, at least for now. So later after estimation, we'll still look at our PP plots. So before we now say, okay, we are good to go with what we have obtained as our result. So that's the conclusion on assumption 4 for now. Then another word for factor, you can use treatment.
Dr. Tekwe, yes? Please, maybe if you can reduce your pace a bit. You know, I think you know a bit fast, and so you can just step down a bit so that they come up. Please, you all have to bear with her. I think you know we all have our style, and then it's a bit difficult for anyone to change just immediately. So please, you bear with Dr. Tekwe, and please just you can just tone down your pace a bit. Thank you.
Okay.
Yes, we'll be able to enjoy our better.
Okay, so thank you very much. So what I just said, I said we are going to take our final decision on the issue of outliers post-estimation. As in, after that post-estimation, we still look at our PP plots. That's examination of our residuals. We want to check whether our residuals are normally distributed. So while checking for the normality of our residuals, we can also check for that outlier. We can look out for it in that plot. So if there's any problem, you will see that it will stand out. It will be alone. It will stand alone. So that you will know that something is wrong with this. Generally speaking, ANOVA is robust to so many of these assumptions that we are talking about. So even if your data set is not that, so it's not following 1 or 2 of the assumptions, you can still go ahead with your ANOVA. That is why you see that most times people use it because it's robust, it's naturally robust to violations of assumptions. So I said for factor is your independent variable, your predictor. Independent variable, you can call it predictor, you can call it independent variable. You can also call it treatment. And it is categorical in nature. So in this example, drug is our predictor. And it has 4 groups, 4 categories. Drug 1, drug 2, drug 3, and drug 4. So thank you very much. So let's continue. So what we are trying to do is to get the estimation. So under this main, you can see the response variable. So the arrow there, response, our response variable is systolic. So go to systolic and click that. Our factor variable is drug. So click drug. Then we need summary tables, summary statistics. So click produce summary table under output. So, and then you click submit. You can see the ANOVA table now. the first thing you will see the summary table. You can see summary of increment in systolic, then drug use. For drug 1, you can see the mean. For drug 2, you can see the mean. Drug 3, that has the lowest mean. Then drug 4. Then the ANOVA table itself. Source of variation. You know, the other time we said ANOVA is the partitioning of the total variability that you have in the system into component parts. So now, the sources of variation that have been identified, they are between groups. We have 4 groups. Between groups, you have that. After that, because it's just one factor, the other one is within groups. So this within groups is the residual error. So we are not going into the details of that because this is not a pure statistics class. But we have said that under one way ANOVA, our independent variable is the factor and it's just one. For this example, we have 4 categories of that particular factor. And then we have our response variable. Our response variables are dependent variable. And it's systolic in this case. Then we have the error term. So if you look at the model now, you see that those groups, the factor now, the factor drug is significant. Probability greater than F, 0.0001. That's significant. So if you run a one-way ANOVA and you are saying that your factor is turning out to be significant, as in you are rejecting H0. What is H0? H0 says all those categories. In this case, drug 1 is equal to drug 2, is equal to drug 3, and is equal to drug 4. What does that mean? It means they have the same influence, they have the same effect, they have the same impact on systolic blood pressure. That is what the null hypothesis is saying. The alternative hypothesis is saying at least a pair, but we don't know the pair. So whether it's drug 1 versus drug 2, or drug 1 and drug 3, once you have at least a pair not being equal, then the alternative hypothesis will hold. So what we are seeing here is that we are rejecting the null hypothesis from this result. 95% confidence level, our alpha is 5%. So we are rejecting that null hypothesis that they have the same effect on systolic blood pressure. So anytime you have something like that, that you have this particular factor to be significant, as it's contributing significantly to your response, that means you have to do another thing. And that other thing is to go for multiple comparison procedures to be able to know which of the groups are different. Do you understand? Okay, so we have to note that. But as we said the other time, we have not concluded on whether our assumptions are okay or they are not. So we need to conclude on that. And for us to be able to conclude on that, we have to go to the other command, and that is the ANOVA command. This ANOVA command has the advantage of enabling us to run prediction tests and other post-estimation commands. So what we do now is to run that ANOVA command. ANOVA systolic, then drug. ANOVA systolic, drug. You can see that the table is a little bit different from what we had before. This one looks like a regression output. You can see model, you can see drug, then you see the residual, then total. You can see R squared, adjusted R squared. The model is significant. That means that all the necessary explanatory variables, all the necessary predictors have been included. Do you understand? All the necessary predictors have been included. And then the drug is our factor. The drug is our factor. And that one is also significant, just like the previous table. It's also significant. So now, just as we said, we now want to get our residuals. Why?
Excuse me.
Yes?
Excuse me, ma. The R squared of 0.3 and the adjusted R squared of 0.29. Sorry, what does he suggest? I think
Please, when we get to regression, we will talk about that in
regression.
details.
Okay.
Yes, regression analysis. What we want to
Okay.
do here is just to generate this table so that we'll be able to conduct our tests of residuals. We need tests on residuals to complete our model
Sorry, madam.
adequacy checks.
Okay.
Do you understand?
Madam, please, can you please? I had some network problems, so I couldn't catch up with the second test that you have done. Can you please?
Which test?
Can the test that you are showing right now? I missed it.
This is the command ANOVA systolic drug. Just type ANOVA systolic drug.
Ma, please, I can't get the data set. I don't know how to get the data set.
Please just type web use systolic. Type web
Ensure
use
your
systolic.
system is connected. If your system
If your
is not
system is, if you are not online, you can't
If
get
you are
the
not
data.
online, you will not be able to get it. Web use systolic. So now that we have this table, what we want to do is to be able to work on our residuals. And our original data set does not contain the residual. If you look at our original data set, there's nothing like residual. We only have drug, disease, and systolic. And for us to be able to check our model for adequacy, we need to work on our residuals. We need to work on our residuals. And to do that, we need this command: predict residual, predict residual, residual, predict residual, residual. So let's check now. You can see that the residual has been added. We have drug, disease, systolic, and residual. Now, this residual is your response minus your fitted value, minus your y, that is yi, minus yi hat. We give you the residual. So this is the residual now. So we want to work with this. So the first thing we would like to do to check if our residuals are normally distributed. To check if our residuals are normally distributed, that is assumption 5. We need to check if our residuals are normally distributed. So to do that, we can pass through 3 ways. Number 1, we can check histogram of residuals. We plot histogram of residuals. That's number 1. Number 2, we can examine the quantiles of residuals against the quantiles of the normal distribution. We can examine the quantiles of the residuals against the quantiles of the normal distribution. Then we can also examine the standardized normal probability plot. We can also examine the standardized normal probability plot. The first thing is we can examine the histogram of our residuals. Number 2, we can examine the quantiles of our residuals against the quantiles of the normal distribution, that is the QQ plot. The last one is we can examine the standardized normal probability plot of our residuals, that is the PP plot. So let us go to the first one. Examination of the histogram of our residuals. Examination of the histogram of our residuals. So we say histogram, residual, normal, then K density, then K density. You have our residuals, then you have the frequencies, the K density. The one that is smooth, that is how the plot would look like naturally if it follows normal distribution. And the K density is how the true population will look like. You know, it's from the true population that we get the samples. How that one will look like, you can see that it's not as smooth as the other one. So merely looking at this histogram of residuals, coupled with the fact that we said that ANOVA is robust to violations of assumptions, is robust. So we look at it, we can conclude that visually what we are looking at looks normally distributed. Histogram of residuals that we are seeing here looks normally distributed, even though it doesn't really look like it's totally normally distributed, but we can take it and work with that. That's a way of solving the problem of are the residuals normally distributed? We can plot a histogram of our residuals. That's the first way. So let's look at the second way. The second way is to plot the standardized normal probability plot. The standardized normal probability plot. So P norm residual. P norm residual. This is our PP plot. P norm residual. We are examining our residuals now via the standardized normal probability plot. If we want to check this, our focus should be on the center. Our focus should be on the center. If we look at what is there, you see that the points seem to lie on the line. They seem to, not everything, but they seem to lie on the line. So, and the other time, we didn't conclude on that outlier. We didn't conclude on it. If you look at what we have here, you see that there is nothing that is standing far away from others as such. No point is standing aloof as such here. If you look at it critically, no point is standing aloof from others as such. So based on that, you see that what we can finally conclude on the issue of outliers is that that outlier that we have there is not a significant outlier. It's not significant, cannot do anything to bias the outcome of our investigations based on these PP plots. Based on these PP plots. So that's that. Another thing that we can do, the third one, is to...
Please, I have a question, please.
Yes. Yes, please.
Yeah, I plotted the graph, the histogram of residuals, and it's quite different from what you got. Like in the bin, I got 7. The bin is 7. The start is 8.75. I got here. Then the width is quite different from what you got. The width here is 2.47.
Maybe which version of Stata are you using?
13.
Well, but if you get everything right, what you have should actually look like a kind of a normally distributed variable.
It doesn't.
Does it look like that?
No, it doesn't.
It doesn't.
Yes.
It doesn't.
Yes, ma'am.
Well, maybe we'll look at that carefully later. Maybe after the class, you look at that carefully. Because if we are using the same data set, then I don't think there should be variations. I don't think so.
Even the P norm, the residual too, the graph is quite different from what you got.
Which data set are you using?
The same data set. I got every other thing right.
Web use systolic.
Yes, ma'am.
Well, we will have to look at it carefully later. We have to look at it carefully because I cannot detect.
I'm also using 13, but I'm getting the same answer you are getting.
And that is you see now. You're having the same issues too?
No.
Okay, you're not having that issue. Okay. Yeah. So that means that something must be wrong somewhere. So we'll look at that carefully later.
All right.
So let's continue, please. So the next thing is to check the contours of the residuals against the contours of the normal distribution. So we type Q norm residual, Q norm residual, Q norm residual, Q norm residual. Here the emphasis is on the tails. The emphasis is on the tails here. If you look at the tails, it's like those values seem to be kind of deviating. And you can see that one very close to that intersection there. You can see it is like it's standing far away from others. You can see it. And then you can see others. It's like they are not like aligning to the line. If you check the tails, you see that one. You see it, that's the outlier. Then you see others too. But by and large, if you look at what you have here, and you have what you have here too, and you consider the other results that you have been obtaining, and you also consider the fact that ANOVA is robust to some of these violations. So you can proceed and then conclude that your residuals are normally distributed. For the QQ, you focus on details. You focus on details. Why for the PP, you focus on the center. So if you look at the two graphs, you see that by and large, you can continue with your analysis, with your estimation. So we have now concluded on assumptions 1 to 5. We have decided now that our residuals are normally distributed. We have decided that our residuals are normally distributed. The last assumption is that we should have homogeneity of variances. We should have homogeneity of variances. Homogeneity of variances, as in we should have constant variance. To check this, from our one-way output for our one-way and ANOVA, you see somewhere there, they wrote Bartlett's test for equal variances. Bartlett's test for equal variances. So it's inside that output. That test is there. And if you look at it here, it is 0.800. Bartlett test for equal variances. H0 says the variances are equal. H1 says the variances are not equal. So now we're accepting H0 that the variances are equal. We're accepting H0 that the variances are equal. But there is a note of warning for Bartlett's test. There is a note of warning for Bartlett's test. If you want to use Bartlett's test, number one thing that you have to note is that you have to ensure that normality of your residuals have been established. You have to ensure that normality has been established, because Bartlett's test is very sensitive to normality issue. And if you're not able to fully satisfy that condition, then it will not be proper for you to go for Bartlett's test. Maybe you have to go for other tests, like a modified Levin's test. Modified Levin's test, I think we have it a robust equal variance test in Stata. Robust equal variance test in Stata. We have it as that. But ordinarily, one of the assumptions of one way and another state that errors should be normally distributed. So that means if that one is satisfied, you are good to go with Bartlett's test. But another thing that must be noted is that you must have large sample size. Your sample size should be large enough. Why? Because Bartlett's test lacks power in small samples. It doesn't work very well in small samples. It doesn't work very well in small samples. So if you want to get good results, make sure that you have large samples. And if you notice from what we've been talking about on this hypothesis test, even from last lecture, we've been talking about the need to have large sample sizes. If you have large sample sizes, most of the problems around all these assumption issues, some of these problems will have been overcome if you have a large sample sizes. So 2 points to note under Bartlett's test for homogeneity of variance. Number one, Bartlett's test is sensitive to normality problems. It's sensitive. So you have to establish normality first before you go ahead with Bartlett's test. If that is not guaranteed, normality is not guaranteed, you can go for another test, like modified Levin's test. Another point under Bartlett's test for homogeneity of variances is that you should have large sample size. If your sample size is large enough, then there won't be problem. It will come out the way it's expected to be. So that's that about all the assumptions. Do you have any question before I proceed? Any question before I proceed?
Yes, I have a question. I understand the. Sorry, ma. Can you hear me now?
Yes, please continue.
Oh, okay. I understand the conditions you gave before we can use the Bartlett test. But from this result we have, what can we conclude? We conclude that from the test, this example you are showing us, does it show that the variances are equal or they are not equal?
The variances are equal. Variances are equal because this is 0.8, 0.800, 0.800. This is a greater. It's greater than our 0.05, our alpha level 0.05. So you accept H0 and conclude that the variances are equal.
Okay.
Thank you very much. So the other time we said when you look at your analysis of variance table and that factor, this is 1 way ANOVA, just one factor, and that factor is significant, like here, 0.0001 is significant. That means you cannot stop there. You need to identify the groups that are actually contributing, that are actually having impact on that systolic BP. You need to identify those groups. And that leads us to multiple comparison tests. That leads us to a multiple comparison test. We can approach the, hello?
Hello, ma. Yeah, sorry, I want to take you back a little. But you said something about the Bartlett test, that the sample size should be large enough.
Yes.
How large enough? Is it 30, like the T-test, or under 30?
From 30. From 30.
Okay, ma. Okay, thank you, ma.
Yeah. So we can approach this multiple comparison test from 2 angles. From this window that propped up the other time when we wanted to run our one-way command for one-way analysis of variance, you notice that under this response variable and factor variable, we have another thing called multiple comparison test. You can see Bonferroni, Sheffer, and SIDAC. Bonferroni, Sheffer, and SIDAC. So you can use any of the 3. They're even more than that. That's why I said we can approach it from 2 angles. So if you, hello? So if you want to use Bonferroni procedure, you just check this box. If your interest is on
mute your mic, please.
Sheffer's multiple comparison procedure, you check this. If your interest is on SIDAC, you check this. So we'll not go into the details of that, but there are advantages and limitations of choosing one or any other one for that matter. But for the purpose of this training, if your interest is on Bonferroni, for instance, if your interest is on Bonferroni, you check that box. Let us produce our summary table. But because we have seen our ANOVA table, we have seen it, we suppress the ANOVA table. You suppress the ANOVA table. You produce summary table, and then you click submit. And then you click submit. You can see the command. The command line says one way systolic drug, Bonferroni tabulate, no ANOVA. One way systolic drug, Bonferroni tabulate, no ANOVA. So the tabulate will give us the summary, just like we had before. And then the comparison. Pairwise, we have 4 groups for drug. Group 1, group 2, group 3, group 4. So here we can see this is 2, this is 1. Comparison of increment in systolic BP by drug use between 2 and 1, between 3 and 1, between 3 and 2, between 4 and 1, between 4 and 2, between 4 and 3. So what this means, it means row mean minus column mean. Row mean minus column mean. The row here is the 2. This 2 is the row. This 1 is the column. So row mean minus the column mean. What we now do is we go to this summary table. Row mean minus column mean. Row is 2. That is, the mean for 2 is 25.5333. And the mean for column, that's 1. That's 26.06667. So take the subtraction. 25 point something minus 26 point something will give us that minus 0.53333. 25.5333 minus 26.06 will give you that minus, this value that you have here in this cell here. Row mean minus column mean will give us that value. The one you have immediately beneath that cell value, that is 1.000, is the p-value. That is the p-value. And if it is 1 point, that means that it's not significant. It means it is not significant. And what that means is that drug 2, we have 4 drug types. Drug 2, on the average, has a lower mean score than drug 1. Lower mean score of what? Systolic blood pressure. Drug 2 has a lower mean score than drug 1. If you look at it, it's lower than drug 1. And that lower mean score that it has, when you look at it, is not significant. It is statistically not significant. Do you understand, please? That is what that interpretation is talking about. Similarly, if we go to 3 and 1, that is row mean minus column mean. The row is the 3, the column is the 1. So for row mean, the mean for 3, the mean value is 8.75 minus the column mean, that is the 26.0667. If you do that subtraction, you get minus 17.3167. So immediately after that, you see 0.001. That's significant if you compare it with our upper level. It's significant. So what it means is that drug 3, on the average, has a lower mean score than drug 1. And that value is statistically significant. What we are saying in essence is that when you compare drug 3 and drug 1, drug 3 has a lower value, mean systolic blood pressure value compared to drug 1. That means drug 1 will give you a higher value than that of drug 3. And that higher value that you have there, what you are saying is that it's significant. Do you understand? That is what it means. If you move to 3 and 2, row mean minus column mean. Again, the row here is 3, that is 8.75. The column here, 2, that's 25.533. If you do the subtraction, you get minus 16.7833. And that one is also significant. It's 0.001. What it means is that drug 3, on the average, has a lower mean score compared to drug 2. And that result is statistically significant. That means that drug 2 will give you higher values compared to drug 3. Drug 1 will give you higher values compared to drug 3. Drug 2 will give you higher mean values compared to drug 3. Drug 1 will give you higher values compared to drug 3. Drug 2 will give you higher values compared to drug 3. Let's go to drug 4 versus drug 1. Drug 4 and 1, that is row mean minus column mean.
Sorry, Dr. I have a question.
Yes.
Observation.
Drug 2 versus drug 1, is it significant?
Drug 2 versus drug 1 is not significant.
Okay.
It's not 1.00. Compare with your 0.05. It's not significant.
Hello, I have an observation to make.
Yes.
So for drug 3, where we have minus 17.31. I was thinking the comparison was between drug 3 and 1, not 3 and 2.
3 and 1 first, before we move to 3 and 2. We first of all treated 3 and 1 before we move to 3 and 2.
Okay.
Okay, so let's now move to.
Sorry, ma, I have a question, sir. Sorry. My question is that I used to do this ANOVA in another software, but it's not the same. It doesn't answer this name that you are. I'm not used to this Bonifere, but it's the same thing.
There are several multiple comparison procedures.
Okay, we used to call it post hoc.
Post hoc, yes, it's the same thing. Yes, post hoc test.
SPSS.
Yes, it's the same thing we are talking about here, please.
Okay.
Yes. Let's continue.
Sorry, madam. I would like to know, how do we know the null hypothesis for the test that we are performing? Because I found that last lesson on normality test, we found that the null hypothesis was the variables are normally distributed. So how do we know about the tests that we are performing right now? How do we know what can be its null hypothesis before we conduct it?
What we are talking about, we are simply comparing the p-values with our level of significance. That one is a constant. If your p-value is less than your level of significance, you will do what? You will reject H0. You will reject H0 and conclude that there is significance. But if your p-value
how do I know the H0 for the test?
For this case, we have our alpha value, that is the reference value, and that is a 0.05. And then this value that you see here, the 1.00, the 0.00, they are p-values. And then you compare p-values with the alpha values. So when your p-value, for instance, this 1.00 here, in this case, it is greater than 0.05. That is our alpha value. If it is greater, whatever it is, whether it's whatever it is, once it is greater, what you are saying is that you are accepting your null hypothesis. But if it is lesser than that 0.05 that is your reference point, then you say you are rejecting your null hypothesis. So what we have here, we have two pairs that we are comparing. We are comparing two pairs. And those two pairs, you are saying that 2 and 1, for instance, 2 and 1, drug 2 and drug 1, they have the same effect. They have the same impact on systolic blood pressure. They have the same impact on systolic blood pressure. And what are you trying to test? You are trying to say that they do not have the same impact. You know what? Where we started from, our analysis of variance table, we rejected null hypothesis and concluded that there are differences, as in they are contributing. At least a pair is different. A pair is not equal. That is what we are saying. So what we are testing now is this pair that we have here now, 2 and 1, the basis, they are equal versus they are not equal. So now that you are saying that you are accepting H naught, it means you are saying that the impact of drug 2 and drug 1 is not statistically significant. It's not statistically significant. It's like they are contributing the same thing. That is what it means. It's not statistically significant. But if it is significant, like 3 versus 1, if it is statistically significant, what it means is that that 1 for 3 versus 1 is giving higher value, higher mean value, is actually contributing significantly. That it means that if you take drug 1, it is most likely that you will have higher systolic blood pressure. That is what it means, because it's significant. Drug 1 is higher than drug 3. If you look at drug 3 and 2, 3 versus 2, the p-value is less than 0.05. And we are saying that on the average, drug 3 has lower mean score than drug 2. That means that drug 2 is having a higher value. And if you look at the mean, it's higher than that of drug 3. And it's contributing significantly to that systolic blood pressure. It's contributing significantly. So if someone takes drug 2, that means that it will contribute significantly to having higher systolic blood pressure. That is what it means. The same thing applies to 4 and 1. We want to know, that's what we are trying to do. We want to know those pairs that are contributing. Our ANOVA table says some pairs are actually contributing to increment in systolic blood pressure. So what are those? What are those pairs? We need to identify them so that we can take decision. Maybe we advise the medical people appropriately or whatever, so we can decide appropriately. So if you look at 4 and 1 too, if you look at 4 and 1, that is 13.5 minus 26.067. That one will give us minus 12.567. Again, that means that on the average, drug 4 has a lower mean score compared to drug 1. If you look at that drug 1 again, drug 1 is higher than drug 4. That is what it means. So when you look at that here, you see that drug 1 is having something to do with increment in systolic blood pressure. Drug 1 has something to do with increment. Even for when you compare with drug 2, it's just that it happens not to be significant in that instance. If you compare drug 1 to drug 3, you will see that drug 1 is also higher. Compare drug 1 to drug 4, you will see that drug 1 is also higher. Look at drug 2, 3 versus 2. Drug 2 is also higher than drug 3. Drug 2 is also higher than drug 4. Can you see that? Drug 2 is also higher than drug 1. It's also significant. But look at 4 and 3. 4 and 3, that is 13.5 minus 8.75. 13.5 minus 8.75 will give us 4.75. And that's not significant. That's 1.00. So that's a positive value. So that group 4, that drug 4 is lower than drug what? That drug, the positive sign that you see there means that row group, that is drug 4, is higher. You can see that 13.5 is higher than the column. What is the column? 3. That is 8.75 is higher. But in this case, it's not significant. So what can we bring out of the one-way ANOVA? Number 1, we have established that the factor drug contributes significantly to increment in systolic blood pressure. We have established that. The next question now is, which of those drugs? Is it drug 1 or drug 2 or drug 3 or drug 4? We have also, through this Bonferroni test, be able to see that drug 1 contributes. When you compare drug 3 and drug 1 contributes. It gives higher mean value compared to drug 3. Drug 1 gives higher mean value compared to drug 4. Then if you look at drug 2 also, drug 2 gives higher mean values compared to drug 3 and is significant. Drug 2 gives higher mean values compared to drug 4 and is also significant. So what are we saying? In terms of inference now, decision making, we'll be on the lookout for drug 1 and drug 2. In terms of increases in systolic blood pressure. And if you want to get those that are lower values, you go for maybe drug 3 and then drug 4. Do you understand, please? That is what the Bonferroni aspect is talking about. It's not only Bonferroni, just like that person said the other time. There are so many types of these multiple comparison tests. If you look at that window, you see that we still have Sheffield. We also have SIDAC. We can also pass through.
Ma, excuse me, please.
Yes.
Ma, does it mean the science doesn't matter?
The science, we have used the science. If you talk about the science is talking about the row group is lower. If it is positive, it means the row group is higher. That is what it means. Because it's row minus column. It's row minus column. So if it is negative, it means the row is lower. If it is positive, it means the row is higher. That is what it means.
Okay, ma.
Okay. So to get some other comparison tests, we can go to statistics. Summaries, tables, and tests. Then summaries and descriptive statistics. Then we go to pairwise comparison of means. From statistics, go to summaries, tables, and tests. From summaries, tables, and tests, go to summary and descriptive statistics. From summary and descriptive statistics, go to pairwise comparison of means and click that. You see another window coming up. So under main, you see your variable, then you see over. Then under that, you see multiple comparison adjustment. So under that variable, choose your systolic over what? Our one factor, over drug. Then under the multiple comparison adjustment, once you pick that arrow, you see that so many things will be coming out. You can see Bonferroni, SIDAC, Sheffers, Tukis, Student Numancor, Duncan's, Dunet. Maybe we are using other version of Stata. You may even have more than that. I'm not so sure. But from what I have here, we have Bonferroni that we had the other time, SIDAC, like the other time, Sheffers, like the other time, Tuki, Student Numancor, Duncan's, and Dunet methods. So let's now take another popular one. That's Tukis method. So choose Tukis method and then go to reporting section. The reporting section. You see the confidence level, 95, 99.1, 99.5, and so on and so forth. But let's leave it at 95. Then let's now click effect tables. Click effect tables and check that box that says show effect tables with confidence intervals and p-values. Show effect table with confidence interval and p-values. So, and then you submit. So you can see the command line. PW means systolic, comma, over drug, M compared to key, effect. PW means systolic, comma, over drug, M compared to key, effect. So you can see number of comparisons, 6. You can see just like we are under Bonferroni. We have here 2 versus 1, 3 versus 1, 4 versus 1, 3 versus 2, 4 versus 2, 4 versus 3. Pairwise is pairwise, just like our t-test, independent t-test for 2 groups. This time around, we are dealing with just 2. So you can see the t. 2 versus 1 is also not significant here. It's not significant. 3 versus 1 significant. 4 versus 1 significant. 3 versus 2 significant. 4 versus 2 significant. 4 versus 3 not significant. You can see that just like we did the other time. So you report based on that too. So you have your reports, and I think that's what we have to say. That's okay. You can pick any other one and just try and take your decision based on that. And so you only do multiple comparisons after you have rejected H0 in your main ANOVA output. You must have rejected H0 there before you move. If you accept H0 there is no need for any multiple comparison. if you accept H naught under your ANOVA table, there's no need for any multiple comparison procedure.
Please come again.
What I'm saying is that for you to use multiple comparison procedure, you must have rejected H naught in your main output for your ANOVA, one-way ANOVA. You must have rejected H naught. If you accept H naught, there is no need for you moving to multiple comparison. There is no need. You just stop there. The analysis stops there, and you conclude that the drugs, they are not contributing anything to systolic blood pressure. But what we have done, the drugs actually contributed to increments in systolic blood pressure, and we wanted to know which of those drugs. So that led us to multiple comparison procedures. So, and we have tried
from these results, can we say that it is these ones that are significant that has contributed to an increase in systolic blood pressure?
What we are saying is that if you look at 3 versus 1, just like we had under Gonferoni, if you check it very well, you will see that 1, the mean for 1 is higher than that of 3. 1 is higher than that of 4, and it's also significant. 2 is higher than that of 3, significant. 2 is higher than that of 4, significant. Even 1 is higher than that of 2, just that it is not significant. Yes, so what are we looking out for? We'll be looking out at drugs 1 and drug 2. Drug 1 and drug 2, because they are the ones that are giving us higher mean values when you compare them to other the mean value of drug 3 and drug 4.
Yes, ma'am.
Okay. So thank you. So that's the end of one-way ANOVA. So let's move to two-way ANOVA.
Hello, ma'am.
Yes.
I have a question, ma'am.
Yes, go ahead, please.
I just need a clarification. I want to know if one should have the same data. If this test should be run on SPP, is it going to give the same output?
I don't understand what you're trying to say. If you run it on where?
On SPSS, sorry.
SPSS.
With this SPSS.
The most important thing is to get the understanding. SPSS can also give you Tukey and Gonferoni and whatever. So whatever output it gives you, what you need to do is to understand how to interpret the results that you have before you. That is the most important thing. SPSS will also bring out your output.
All right.
Do you understand? Okay.
Thank you, ma'am. Yes, very well.
Okay. So I'm clearing, but you may not, but I'm clearing. So I'm still going to use web use systolic. I'm clearing because of that residual aspect. You know, we have created another variable residual. So I'm trying to remove that. So I clear, I retype web use systolic, because this is the data set we're also using for our two-way ANOVA. So clear and type web use systolic. Make sure you are online. Clear, then type web use systolic. Make sure you are online so that you get it.
Okay.
Okay. So two-way ANOVA is an extension of one-way ANOVA. One-way ANOVA has one factor or one predictor.
Please, ma'am.
Two-way ANOVA. Yes?
Please, ma'am. I have a question.
Yes.
If after the summarize of your quantitative variables and qualitative variable, you see that the outlier is significant, how can we do in this case?
You go back now. You cannot just remove it anyhow. You have to go back to your data set. You examine it carefully before you decide that what should I remove it? Should I do something to it? Should I, before you take any decision on that outlier, you have to check first. Sometimes
okay. If I remove the size of my sample will reduce, that can affect my work in my regression or
that is what
something.
we are saying. That is what we are saying, that you don't do that anyhow, because it may be a genuine observation. So if it's a genuine observation, there's no need removing it. You go ahead, just like we did here. We didn't remove it here. We just continue. And we have said that ANOVA is robust to some of these violations. So even if you have something that is like that there, if there are not too many, ANOVA can still accommodate it. Do you understand? Okay.
Yeah.
So excuse me.
Thanks.
Two-way ANOVA.
Excuse me, I have a question, ma'am.
Yes, please.
Concerning the normality, when we check for the normality of the residual, you you said you have three methods that we can use for that: the histogram and the QQ plot and the PP plot. So I want to ask a question because last week when the prof was taking us through the class, when he said when checking for the normality that we have three processes that you can use using the skewness and the kurtosis, the Sapiro and something like that. So I want to ask, is it the most that when checking for the normality of the residual that we should go through all this either of these processes, or we can also go through the skewness, kurtosis, and well, that is what prof taught us last week.
Actually, some people will advise that you check that your Y, your dependent variable, is normally distributed. And if you want to check that, you are not checking for the residuals. You just check. So you can use your S-Wilk, S-Francia, and your histogram to check that for normality. But theoretically speaking, from the angle of theory, if you want to check, if you want to do model adequacy checking, not just checking whether your data follows normal distribution, that one is a little bit different. It's a little bit different. If you look at the assumptions, we said you check whether the errors or the residual, they're the same thing, error or residual are normally distributed. So you cannot, it's not that you cannot check whether your dependent variable is normally distributed. You can check that. So if it's normally distributed, so there's every probability that the error terms will also be normally distributed. There's every probability, but theoretically speaking, you check whether the residuals are normally distributed. That is why we have to pass through the residual analysis. That's what we call it. We call it residual analysis. So we pass through that approach. So if you just check for the normality of your dependent variable, well, you can get that those ones also, just like you said, you can get it. That is not in the context of what we are trying to talk about now. We are talking in the context of model adequacy checks via residual analysis.
Okay. Thank you, ma'am.
So let's quickly go to two-way ANOVA. So it's an extension of one-way ANOVA. So instead of having one factor, you have two factors, as in two predictors. Those two predictors are also categorical. They're also categorical in nature. So again, you have, and what are you trying to do? You are trying to check whether those two predictors are contributing. They have impact on the dependent variable, your response variable that should also be continuous or quantitative in nature. So you are trying to check whether they are having impact on that. Apart from that, you're also trying to look at the interaction between those two predictors. The interaction between those two predictors. When you want to select your predictors, select carefully. Make sure you actually select predictors. You know, there are instances where you have grouping variable. You have grouping variable as the second one. It's not actually the second treatment or the second factor. It's just what you have used to group. It's not actually the factor. You know, the factor or the treatment is what you apply to get a response. It will elicit a response. So that you choose that carefully. So that you are not choosing block. You are not using block as your factor. Because if you have that, you have your block, then you have your treatment, you are still under one way. You have only introduced blocks. So that one is quite different from what we are talking about here. We are talking about two genuine factors, two predictors that are actually, you're actually trying to check whether they have anything to do with the response. Because if it's like something like a block, it will not be contributing anything to the response. You have just used it to just break down into groups. You have used that to just break down into groups. So that one is not the genuine something, the factor that we are talking about. The factor that we are talking about here should actually be contributing, should actually be seen that it has been applied to something and you are getting response from it. So two factors. Then you check the interaction of those two factors on the response variables. As usual, we have the assumptions. Dependent variable should be continuous. Independent variable should be categorical. Observation should be independent. There should be absence of significant outliers. Residuals should be approximately normally distributed. Homogeneity of variances. So let's quickly check. Just like we said, assumptions 1 to 3, they are from your study design. For independence of observations, please ensure that randomization procedures have been strictly followed so that is satisfied. So for number 4 now, we examine box plot again. Examine box plot. Graph box. Systolic over drug over disease. You can see now that you have disease, 3 groups. Okay, you have drugs, 4 groups. Drugs have been nested inside disease. Then you have the four groups inside the disease, four drug types inside disease 1, 4 drugs are inside disease 2, 4 drugs are inside disease 3. Again, you can notice the outliers for drug 2 and disease 2, drug 4, disease 2, drug 4. You notice one systolic value around that positive range up, one below the 0 value, that's negative. Then disease 3, drug 1. You notice another one too, up, then another one down. So you have that. Then if you look at those median values, if you look at those median values, you see for disease 1, you see that those median values tend to be reducing. Drug 1, drug 2, if you look at those median values, something like that. And if you look at the length of those boxes, the length, you see that there are variations. There are variations. So we can see variations generally in the data set. So let's now move to the analysis. The analysis to actually examine whether those variations, whether they have something to do actually significantly with the systolic blood pressure, whether they have something to do. So just as we said, we still check for these outliers. Let's type our SU, summarize command. Again, just like we had the other time, that one is the only one, because you see the others, they are in the range of the other ones. The other ones that are above, the positive ones, they are still within the other values. The ones that still seem to be kind of different is this -6. Others, if you look at them, you see that they are still kind of within where the other values congregate. So this -6. So just as we said, we still look at our PP plot later, and we have a robustness of our ANOVA to actually deal with. So let's go ahead with that. So for that, let's go to statistics. Statistics, linear models and related, then ANOVA stroke MANOVA, then analysis of variance and covariance. From statistics to linear models and related to ANOVA stroke MANOVA to analysis of variance and covariance. So you see another window now. You see another window. Under model, you can see dependent variable. Our dependent variable is systolic. So you see the 3 dots here. 3 dots. Can you see the 3 dots? So click the 3 dots. When you click the 3 dots, you see another window. You see another window. Create variable list with factor variables. I think there are some differences here depending on your Stata version. If you look at Stata 12, if you are using Stata 12 or thereabouts, you just see factor and simple variable. But if you are using something like Stata 14, if you use Stata 14, you have more than that. You have more than that. Then you also see where you have add factor variable here and term, you see specification for Stata 14. But not to worry. If you are using Stata 14 and above, under that specification, just go there. You see where you have that arrow, just click it and choose two-way full factorial. Under specification, go to the arrow there, just click it. You will see two-way full factorial. Just choose that two-way full factorial. You see others, just select that two-way full factorial. For those that are having this type of a window, under add factor variable then term, you see the arrow there. Again, choose two-way full factorial. Then under variables, variable 1 is drug. Choose drug. Variable 1 is drug. Variable 2 is disease. Variable 2 is disease. Then click add to variable list. Add to variable list. Add to variable list. Add to variable list. Then okay. When you do that, you return to the previous window and you see that under model now drug # disease. Under model, you see drug # disease. Some of square is still partial. So you click submit. Click submit. And then you have your ANOVA table. You can see the command ANOVA systolic drug # disease. ANOVA systolic drug # disease. If you also type, ANOVA systolic drug disease, then drug #, one #, drug # disease, ANOVA systolic drug disease, drug # disease, you get the same output. But the difference is that we are just moving straight to that without typing the drug disease in the first case. We just type ANOVA systolic drug ASH disease. ANOVA systolic drug ASH disease. We give us that two-way ANOVA table. And look at the model. The model is significant. The model is significant. That means that all the necessary explanatory variables are being included. So you can see that the expectation for the means, the assumption concerning that has been satisfied. You can see drug is also significant, 0.0001, but disease is not significant at 5% level. Drug, interaction between drug and disease is also not significant. Interaction between drug and disease is also not significant. So just as we said the other time, if something is significant, it tells you that you should investigate more. You should investigate more. Like drug, now there are 4 categories in our drug. So we need to do some other investigations on that drug. And that's, before we do that investigation, let us conclude our model adequacy checks. Let's conclude our model adequacy checks. So as usual, let us predict, residual. If you check now, you see that the residual is back. Predict residual is back. So the next one now is to go to our histogram of residuals. Histogram residual. Histogram residual, normal, K, density. You can see the normal plot, then the K density plot. So clearly it looks like normal distribution. The curve looks like a normal distribution curve. So if we look at our P norm residual, you can see you focus on the center. Focus on the center when you want to check. You focus on the center. They are not exactly on the line, but very close to the line. And you can see those ones that are the outlying values, they are not actually very far away as far as this particular graph is concerned. So the next one is a Q norm, quantile of the residual versus the quantile of the normal distribution. You can see that one here. You can see this one also here. You can see this one too. You can see. You look at the tails. They are not exactly on the line, but you can still go ahead and conclude that they are normally distributed. So just like the other person said the other time, if you check that's your dependent variable for normality, whether you use your Shapiro wheel, if you use your Shapiro wheel, or you conduct your histogram on that your normal, or on that your dependent variable, if it's normally distributed, it kind of boosts what you have there. So it kind of boosts it. So, but as we can see from what we have done, we have looked at the histogram, we have looked at the P norm, we have looked at the Q norm. So we can conclude that our errors are normally distributed. Then for the test on homogeneity of variance, we just type E stat X test. This X is for heteroscedasticity. So if this one is a post estimation, this E-stat test will do that for fitted values. So you can see Bruch-Pagan stroke Westbach test for heteroscedasticity. Heteroscedasticity means you have more than one. They are not constant. Heteroscedasticity, more than one. Homo means one, just one constant variance. So H0 for this hypothesis is you have constant variance. H1 means they are not. So for this test here, we have used fitted values of systolic, and it's showing us that we can accept H0, that there is constant variance. You have constancy of variance as far as this systolic is concerned. You can also, if you suspect that systolic, the systolic is our dependent variable. If you actually want to test whether you have constancy of variance in that dependent variable, you can type E-stat X test, E-stat test, then systolic. So So the variable here is systolic. H0 is still, we have constant variance. And if you look at the decision too, you see that we are still accepting that there is a constancy of a variance. You know, the assumption, theoretically, the assumption says that the error variance should be constant. And that implies that that dependent variable, the variance of that dependent variable should also be constant. So it's either you say the error variance should be constant, or the dependent variable itself, the variance of that dependent variable should also be constant. The variance there should also be constant. So we have tried the two here now, and we see that the constancy of a variance has been established. If you want to go via the menu, it's a lot of steps. It's a lot of steps, especially for Stata 14. It's a lot of steps for Stata 14 and others. That's why I didn't include it. I just believe that this one is very straightforward, just like your P norm, residual, Q norm, residual. Just type this started test, your dependent variable, and you are good to go. But if you want to pass through the menu for Stata 14 and above, that means you're talking about from statistics to post estimation to so many other steps that you follow, other reports, summarize estimation samples, you launch so many. But if it is Stata 12, you just move from statistics, go to post estimation, from post estimation, go to reports and statistics. You see the window coming out. So under that, you see test for heteroscedasticity. You can see. So you have Bush-Pagan, so Cook, Westback. If you choose fitted values, just as we did the other time, you submit, you get your results. If you choose the specific variables, specific variable is systolic, then you submit. So you get the same result. But if you Stata 14, you move from statistics to post estimation. From post estimation, move to other reports. From other reports, move to summarize estimation sample. Summarize estimation sample. From summarize estimation sample, then you launch. There's a place to click launch. Click launch. Then from the launch, you see that window, start post estimation statistic for ANOVA. Start post estimation statistic for ANOVA will be displayed. Then there you click test for heteroscedasticity. That's for your test. So then you specify as usual. So that's that. So now, we said that we should when you reject, that means you have to move from your main analysis. That means you have to move on to get further indication of what is actually happening in the data set. So what we now want to do is only our drug that is significant. So we want to move via the margins command, using margins command to check what is actually happening. So we just type margins, drug. We are choosing drug because it is the only significant one. We can test others too, just to see how the whole thing looks like. Margins drug. Can see? Margins drug 1, drug 2, drug 3, drug 4. You see the marginal means. Drug 3 has the list. They are all significant. Yeah, they are all significant. Then we want to see the plot now. So we just type margins.
Sorry, ma, please, what are we doing now?
From our main two-way ANOVA table, it's only drugs that came out to be significant. So since it came out to be significant, we want to examine that particular factor further to be able to interpret that significance. We just say we conclude that drug is having significant effect or significant impact on increment in systolic blood pressure. That is our conclusion. But how? What can you say further about that drug? Since drug has 4 categories, so we want to say some other things about drug. That one now leads us to the margins command. So just type margins drug. It will bring the drug 1, drug 2, drug 3, drug 4, and it gives you the marginal means and tell you whether they're significant or not. Then want to get the plots of the margins now. So type margins plot, no confidence interval. Margins plot, no confidence interval. That's no side. You can see this plot now. Predictive margins of drug. You can see drug use. The linear prediction is actually the increment in systolic blood pressure. You can change that from your graph, using your graph tools. You can change that. Systolic blood pressure. Okay, so you see drug 1, drug 2, drug 3, drug 4. So you see that those that are using drug 1, they have high systolic blood pressure. Drug 2 is kind of higher than drug 1. But if you use drug 3, it gives the lowest systolic blood pressure. After drug 3 is a drug 4. After drug 4, you go to drug 1. The highest is drug 2. Can you see now that we are able to get further information? Apart from saying drug is having a significant effect on systolic blood pressure. How? Drug 3 will give us the lowest increment in systolic blood pressure, while drug 2 will give us the highest increment in systolic blood pressure. That is the further information that we can get. We are doing this because it's only drug that is significant, just as we did under our multiple comparison. You deal with those that are significant. But for instance, if we don't mind, let's try the margins. Margins, we are just trying just to illustrate how it works. Margins, disease. Margins, disease. This is something that will come out. Then margins plot. Margins plot. Margins plot. No sign. That's no confidence interval. This is for disease. It's not significant, so actually you don't report that, but this is what is actually happening. Those that have disease 1, they are the ones that have the highest systolic blood pressure. Those that have disease 2, they are around this point here. And those that have disease 3, they are the ones that have the lowest systolic blood pressure. What about the interaction? What about the interaction? Margins plot, margins, margins, margins. Then you talk about drug and disease. Drug and disease. Margins plot, drug and disease. So this is what you have. Again, margins plot, no confidence interval. You can see now that you have disease 1, disease 2, then disease 3. There's interaction between, you can see the intersection crossing, that interaction between disease 1 and disease 2. Interaction between disease 1 and disease 2. There's also interaction between disease 3 and disease 1. Then disease here too, there's something crossing here too. Interaction between, this color is disease 2 and disease 1. Disease 2 and disease 1. But this disease 3 and what now? Disease 3 and disease 2. Disease 3 and disease 2. Disease 3 and disease 2. Okay, this is disease 3, this is disease 2. But they are not significant anyway. We're just trying to show. So if parameter they are significant, I've given you the commands that you will type to bring out the graphs that will enable you to interpret. But as you can see from our graphs, we are able to show the ones that are significant, like the drug, that okay, this, and I think that is all. If you want to go through the menu too, it takes a lot of steps. It takes a
Please,
lot of steps.
can we see the last 2 commands that are comparing
the last 2 commands? Okay. The last 2 commands, you have the disease. Disease first, margins disease, then margins plot, no confidence interval. Immediately after margins, then the variable, margins disease. Immediately after you show the plot, margins plot, no confidence interval. If you don't put that no confidence interval, it will bring out the confidence interval for you, and you don't really need that as far as interpretation is concerned for this type of thing we are doing anyway. So margins plot, no confidence interval. Then after that, margins, drug ash disease. Immediately after margins, drug ash disease, then you go to margins plot, comma, no confidence interval. That will also bring out the graph. Thank you very much for listening.
Thank you, ma.
If you have question, please, which question we have exceeded our time.
Okay, please, ma, can I ask a question based on the last assignment?
The last assignment, yes.
I discovered that
I'll post the solution. But say whatever you want to say, please. Go ahead.
Okay, I just inputted the commands and then I plotted the graph. I noticed that my graph was totally different from every other person's own. I didn't have any histogram and all of that.
That means you didn't impute the commands carefully. What we just have to do is just to impute the commands carefully. Nothing special, nothing spectacular, but just impute the commands carefully. That's all. But I think I should post the something. So be able to see from that angle.
Hello.
I think instead of posting the commands, though someone taught me how she went about getting, but instead of posting the commands, it's not better to manually execute the commands for everybody.
The commands are there, just like we have been typing. It.
I mean, going through the interface to like.
You don't have to go through the interface. The commands are already there, just like we are typing these ones too. We are not going through the interface. Just type it. We didn't go through the menu. Just type the commands. That's all. I just gave the command just for people to follow it carefully.